Thank you very much. It's a great pleasure to be here. It's actually my first time in Toronto. And I have been doing a lot of work in PDEs and also particle methods, gradient flows, and a bit of optimal transport. So this is partially an overview talk to share a bit how, well, to tell you a bit about conditional sampling and then how optimal transport or non-optimal transport can come into conditional sampling as a tool, as a method. And then I will talk about a specific transport map, the Knothe-Rosenblatt map or KR map. That is a very useful method in conditional sampling. And I will explain why. And then towards the end, I will also talk about a recent work together with Ricardo Baptista, who's here in the audience. And in fact, we just submitted what I'm going to be talking about on arXiv at lunch today. So it should be online, hopefully this evening or tomorrow morning, if it goes too quickly, so then you will be able to check the details of what I'm saying. So yeah, I mean, the director of Fields Institute told us to work hard. We already achieved one paper as part of the meeting. And this is flexible. I would like this to be also interactive if you have any questions. So I put here an overview of what I would like to talk about. I don't have to talk about everything. I can skip a few things. I can spend more time on some other things. So feel free to interrupt me. And at the end, I will talk a bit about some open problems, since we will also have the open problem session later today. And I very much look forward to that. Okay, so without further ado, let's jump straight in. I already wrote a few things on the board to be a bit faster. So why may we care about sampling conditionally? So even just sampling without conditioning, just sampling from some target distribution is a very difficult problem. And there's many, many different algorithms that are trying to do that in different ways, depending on what are the properties of your target. But in many applications, you actually care about sampling from a conditional distribution, not just sampling from some given target distribution. And sometimes that can be even harder. So one area where that appears is Bayesian inverse problems. And of course, there's many, many applications of Bayesian inverse problems, geophysics, also more broadly, the geosciences and medical imaging, weather forecasting. There's many applications. Data assimilation. So, okay, in an inverse problem, usually you do not have a dynamic evolution. So you have some forward map. You have some parameters that define your problem. You have a way of observing, measuring something about your problem, and then you try to infer the parameters from your observations, right? Now, you can also have an underlying dynamical process. So let's say you have something that evolves, right? It could be the weather of the globe, if you want. And you don't know exactly what state that system is in at any point in time, but you have some way of observing it or measuring it. And then you try to infer what is the most likely state of your system at any given point in time, given the observation that you have of that system up to that time. And so what you're essentially doing is you're looking at conditional probability distributions. So this, any kind of filtering algorithm is trying to do exactly that, right? The ensemble Kalman filter, particle filters, stochastic map filters that Ricardo worked on. So you basically evolve forward the conditional probability distribution of where's the state of your system, given all the observations that you were able to make of the system up to that point, right? So for that, you essentially want to sample from the conditional probability distribution. Then there's data imputation, where basically you have some missing data, but you also have some other variables that you can observe. And so you're trying to infer your missing data from the variables that you can observe, right? So that's, again, a conditional problem. Then generative modeling has conditional sampling all over it. So basically in generative modeling, you say, I have some samples from some distribution that I don't know, and now I want to generate more samples. But nowadays, often maybe the applications you can think of, you write a prompt in some text box of an algorithm and say, I want an image of a cat, or I want some nice scenery, right? So you enter a text prompt, and then what you get back is some image. So that's also conditional sampling, because you sample from an image distribution given some prompt, which is often text. I mean, this is just one example, but there's many examples. And Ricardo will give a talk tomorrow, which will talk about all of these, about specifically these applications of conditional sampling in more detail. To do that, there is now a whole sort of family of algorithms that can generate conditional samples in the context of generative modeling. For instance, conditional GANs, where you replace sort of the adversary and the discriminator with conditional distributions instead. And then there's also conditional score-based diffusion models. So yeah, I think Ricardo will say a few more things about this tomorrow. And then also very classical algorithms like the Gibbs sampler. Basically, what there you're doing it the other way around. You want to sample from the joint, and you do that by sampling from conditionals. So if sampling from a very high dimensional joint distribution is very difficult, what you can do is basically go coordinate by coordinate. You condition on all the other coordinates, and then you just sample in one dimension. Now you have reduced the dimensionality of the problem, right? But you still have to do conditional sampling. So basically, all of these are to say, there's many, many instances where you want to do conditional sampling. So how do you do conditional sampling? There's many approaches, but transport can help. So this is why, as a next step, and this is going to be sort of really key for the rest of the talk, is how can you use, so I said measured transport, because this is both optimal transport and non-optimal transport, and I will explain in which sense I mean that. Yeah, maybe before I go there, let me give you a bit more detail on the Bayesian inverse problem side of things to set up notation, so that you have sort of a concrete example in mind that you can take along the journey here of what we're trying to do. Okay, so let's say Bayesian inverse problems. So I'm going to write a very general form of Bayesian inverse problems. So I'm going to write y equal to g of theta. So here, theta, let's say, is in some rk, is the parameter. And that's what we in general don't know. That's what we want to infer. Then y can live in a different space, are our observations or the measurements. And then you have this map G that goes from Rk to Rn. That's usually the observation map or the forward map. There's different names for it. Let's call it the forward operator. And there's sort of infinite dimensional analogs for all of this. But you know, if you have functions that you want to approximate, you can also discretize them in whatever way, taking some basis. But then our measurements are often noisy. So I'm going to add some noise here. And let's assume for now that the noise is Gaussian. With gamma times identity as a covariance. You can also make that more general. So if you have that set up, so what we want to do is basically knowing this G, knowing the noise distribution, and knowing our observations, our data, we want to infer the theta. And we can do that just using Bayes' theorem. So what we want is the conditional distribution of theta given y, right? But what's easy to write down is the conditional distribution of y given theta, and that's the likelihood. So y given theta, I mean, is simply, let me write it out one more. 2 pi gamma n over 2, and then e to the minus 1 over 2 gamma y minus g of theta squared. right? Yeah, I think that's it. That's the likelihood. And now if we also put some prior assumption, we can then get the posterior. Let me just write the posterior directly. So that's what we actually want is what's the distribution of the parameters given the data that we observed. So that's just Bayes' theorem, right? So we have our likelihoods times the prior. Okay, so the distribution of the data, we usually have that. You need to make some choice of the prior. So often Bayesian inverse problems, that's also chosen as a Gaussian. And then this one, you have it given, right? And so now you want to sample from this conditional probability distribution. So this would be uncertainty quantification. What you want to do is basically sample from this distribution. And you have to think in, for instance, if this is in the context of most applications, this forward map G is very complicated. So this could be a black box, maybe a numerical solver for several coupled PDEs. Like this theta could be, you know, some boundary coefficient, diffusion coefficient, and then you stick that in. You can run your solver. For any theta, you can compute the G of theta, but it might take you a few days and a lot of money on some computing cluster, right? And so you also want to come up with algorithms that can do that efficiently, ideally even without too many evaluations of the forward map. So yeah, so what we want to do is efficient conditional sampling. So even if, let's say, we magically had some way of sampling from the joint probability distribution of y and theta, that still doesn't just give us samples from the conditional distribution easily, right? And then you also have many applications where actually the priors are known or the likelihood is very difficult to compute. Or maybe you don't even know these distributions, they're only known through samples, right? That can also be the case. And then you try to have estimators and you try to have theoretical guarantees. And we already heard a few talks that go in that direction. So I hope I convinced everyone that conditional sampling is useful and also that it's a pretty challenging problem, actually, in general. Okay. Now I think I can move towards how to use transport in this. So there's a very nice overview. Maybe I just give the reference here in case people want to check this, by Yusuf Mazouk and collaborators. I hope I get these names correct. Spantini. All right. There's also some recent work by Ricardo actually that also explains the same procedure. But okay, so let's start by fixing some reference measure. Eta. So I'm going to be using this notation with the y and the theta, but you can think of, so this is going to be a distribution of y and theta, but you can also think of this couple of just being x, and then you're splitting it in some way, right? Like you take some coordinates of the x that correspond to the information that you want to condition on, essentially. But because this is a reference distribution, we can choose it. So we can literally pick it whatever we want. You will see later how that comes up. And what we want to pick it as is something that factorizes between the thing that we want to condition on and the rest. So I'm just going to call these eta y and eta theta. For instance, if we choose a Gaussian, it will have that property and you're fine. Gaussians are always a really good choice for reference distributions. And now we want to find a transport map. So this is going to be from D plus K if I use the notation from above. So it's from the joint space. So you want to find a map, a transport, such that there's 3 conditions that are satisfied. I'm going to write them out. So the first condition is that this T pushes forward eta to rho. And here rho is the measure that we're actually interested in. So let me say rho is the joint here, which is proportional to, for instance, my likelihood times the prior, right? If I go back to the Bayesian inverse problem setting. Okay. Now, the second condition is the really crucial one. I'm going to have to cover this. The second condition is that my map has a triangular structure. And this is what is going to make this whole thing work. So I have a first component that depends on y, and then I have a second component that depends on y and theta. And this is basically in R. So the y is in Rn, so this is in Rn. Oh, I switched from D to, okay, let me try and be consistent. And then this would be Rk, right? So the important point is basically that the first n coordinates do not depend on theta of the map. And then the third condition is that for all given y, there exists a unique point z, y, such that this first component of the map can be inverted at that point. So for each y, I can find the inverse point of this. So these are the 3 conditions that we need. So why do we care about these 3 conditions specifically? Because then we have some really nice property, and this is really elementary. I mean, you can check this from literally just the definition of a push forward map and so, yeah? For now, let's say no, but when you care about approximating it, then yes. I mean, it also depends on your measures, right? And the nice thing is that your reference measure, you can choose it as nice as you want. So already with that, you can compensate certain things, yeah. Okay, so what do we have then? So first of all, is that, so this is now the y marginal of the joint distribution. Oh, I need to renormalize, I guess. No, it's fine. Okay, so this is the y marginal of my joint, right? This is equal to the push forward of just the first component of the map of the eta y. Okay, so that's very nice. And then the other thing is that theta given y is equal to t tilde 2 of zy push forward eta theta. So both of these are sort of elementary things that follow from this triangular structure. But now this is obviously really nice because this gives us a way, this gives us direct access to the conditional via this T2, so the second component of the triangular map, and the eta theta, which we have chosen and which is nice, right? And so this directly allows you to write down an algorithm for sampling, for conditional sampling. So let's say we have already some transport map T that satisfies these three conditions. And let's say we are given our data. So we know what we want to condition on. That's what we want to condition on. And then we just do three simple steps. So the first one is we solve this equation to get zy. So get zy. Once we have the zy, or okay, sorry, separately, we just sample many times as we want. Let's say capital N times from the eta theta. And this can be done very efficiently if you choose this to be a nice thing. And then the only thing is left to do is evaluate our second component at all these points. And then these will be samples from the conditional distribution. This is super simple, and it's very nice, right? Okay, so there's caveats here, right? First of all, I didn't say anything about how I'm going to get this T, right? So this is assuming that I have some efficient way of actually getting my hands on such a T. Second complication is you need to actually compute this zy. And often this T tilde 1 is nonlinear. And so you have to solve a nonlinear equation, which also costs you something. So here, this is everything that I've written is for general maps. They do not have to be optimal. I'm not talking about optimal transport maps, right? I mean, the fact that we want this triangular structure already tells you that they're not optimal, most likely, depending on the problem. But next, I want to talk to you about a specific map, this KR map, that satisfies all of these conditions. And the reason why it's very nice is because for the KR map, this first step, so solving this equation with the Z1 has a very explicit recipe where you're guaranteed that you can always write this down. Okay, any questions? Yeah. I haven't yet, okay, I said algorithm, but yeah. So I mean, first of all, you need to get the map, right? So there's the complexity of getting the map. Then yes, for here, I mean, you just need to sample from this guy. So this can be done cheaply. I think the complexity is basically getting the T and inverting this equation. And there's many ways of how you could do that. And in practice, you would never try and do this exactly. You would try to do it approximately. And then depending on how you approximate, that will greatly impact your complexity of the algorithm. Yeah. Okay. Mm-hmm. Yes. Absolutely, exactly. So there's a very nice sort of flow perspective where you can get the map out of flows. And I think that's a very promising direction for this. Absolutely. Okay, then maybe let me go here. Let me talk about KR maps. So Knothe, or Knothe, depending on how you pronounce it, actually introduced this map in 1957 to study convex bodies and in particular the isoperimetric inequality. So Imut Burchett here would know a lot about this, I think. For instance, to solve the Boden-Minkowski inequality. And then completely independently, in a very different context, Rosenblatt also proposed this map for sampling from high-dimensional random variables. And this was in 1952. So both were sort of in the 50s. So this map has been around for a long time. And so this is why it's now known as the Knothe-Rosenblatt map or KR map. Sometimes called the KR rearrangement, and you will see in which sense that's a rearrangement. And the nice thing about it is that it's very explicit. So 3. So I first want to sort of give you an idea what they are. And the easiest ways to do that is to just tell you the construction. So I will actually go in detail through how to construct it. But on a high level, what all it is literally you rearrange monotonically the marginal distributions of just one coordinate. First the first coordinate, then the second coordinate, and so on, and you keep going. So it goes dimension by dimension. So let's do the construction explicitly. So let's take 2 probability measures, and let's assume for now that they're absolutely continuous with respect to Lebesgue. And I'm going to denote with a superscript k the marginal of the kth coordinate. So this is xk marginal. And the pi of x is just of x1 up to xd is just xk. So it's just a projection on xk. And then you can also take conditionals. And what we want to do is we first want to take the marginal on the first 1 to k plus 1 coordinates, and then condition on the 1 to k coordinate. So when I'm conditioning, I'm going to put in small subscripts on the bottom, the variables that I'm conditioning on. And so this is basically the disintegration with respect to x1 to xk. So if I take x1 up to xd, so the whole x, and I sample it from mu, then the xk plus 1 given x1 up to xk is sampled from this guy. That's maybe the easiest way how to describe what this is. So I first marginalize for the first k plus 1, and then I condition on the first k. So I have something that's only a function in the xk plus 1. Makes sense? Okay, so with the setup, we can now go ahead and construct the map. Okay, so as I said, we go coordinate by coordinate. So let's start with the first coordinate. So this is the monotone decreasing such that it pushes forward the first marginal of mu onto the first marginal of nu. So essentially, this is 1D optimal transport. And we already saw that there's always a unique monotone map that solves that, which is given by the CDS, by the cumulative distribution functions. So it even has an explicit expression, right? So actually, the T1 is T1 minus 1 composed with F1, where the F1 is the CDF of the first marginal of mu, and the G1 is the cumulative distribution function of the first marginal of mu. Okay, and then you keep going. And this is where the conditioning business comes in. So, sorry, no, this now goes from R2 to R. Sorry. So this is again monotone decreasing such that, so now this is going to be a function of x1 and x2, but I'm going to condition it on x1 and think of it as a function only in x2. And then I push forward. The first I take marginals in the x1 and x2, and then I condition on x1. for both mu and nu. And then again, I have a one-dimensional thing. And then again, I can find this map, which is going to depend on x1. And then, so, you know, this is unique, and you keep going. And then your last map is going to be something from RD to R. Same thing, such that this TD of x1 to xd minus 1. Now, this is a bit tedious to write, but I guess you know what I mean. xd minus 1. Okay. And then we define Knothe-Rosenblatt map, which I'm going to call TKR, from RD to RD, as this triangular thing, which is T1, X1, T2 of X1, X2, up to TD, X1 up to XD. Right? Okay, that's it. That's the Knothe-Rosenblatt map. And you see that, okay, now we can check whether it actually satisfies, I still have them here, excellent. We can check if this construction satisfies these three assumptions. And you can see that, yes, it pushes forward the mu onto the nu by construction. Basically, that's a consequence of just disintegrating all the things that we transported. It has this triangular structure even more, right? Because I don't even need to specify at which coordinate I do my cut between the y and the theta. It works for anything because it's a fully triangular structure. And then because of that, because of the fully triangular structure, I can invert everything. It's invertible, and so this is also fine. Okay. And it's unique. Yes, here I'm assuming that we're absolutely continuous. Yes. Yes, yes, yes. Yeah. Haha, absolutely. So you're hitting the nail on the head. Exactly. Yeah, we'll get to that. A composition of? Yeah, yes. there is, I mean, yeah, the dynamical formulation of this. So these triangular maps correspond to triangular velocity fields. And then if you do particle transport with the triangular velocity fields, then that's what you're doing. You know, I don't know exactly if that's what you mean, but yeah. And then those triangular velocity fields relate to this flow approach that you mentioned. Comes up in the yeah, flow matching approach for generative models. Okay, so the big question is, how are you actually going to find this map? Okay, so in some sense, this is a stupid question because I just told you how to construct it. But as you said, this involves basically computing all these CDFs, right? Conditional, which have therefore integrals in them. That could be very high dimensional integrals. So especially if this is high dimensional, this is very expensive to compute. It's explicit, you can do it, but it's very expensive, right? So actually in practice, maybe you don't want to be doing this. So what you want to do is have an approximation of this map that is efficient in some way, and that is a good approximation for the application that you care about. Okay, so one approach to get around this is to notice the following. And this very nicely links to one of the other talks we had just this morning. So what we can do is approximate. Okay, so idea, let me write like this. One idea is to solve instead a variational problem I'm going to take the min over all the maps in some class, which I'm going to define in a moment. And I take the KL divergence of T push forward mu given some mu. And so what's this class now? So this curly T is all the convex, or yeah, this is a cone actually, convex cone of monotone, non-decreasing, lower triangular maps T from RD to RD. Doesn't that classify as a shape constraint? The way that we saw this morning. So why this? So with this choice of class of maps, you can actually show that the unique minimizer of this problem is exactly the Knothe-Rosenblatt map. So the unique min is T equal to TK. Oh, I shouldn't put an exclamation. Okay, so this gives you now also a computational tool to actually say, okay, maybe we don't care exactly of having the KR map, but maybe we can approximate it using this variational formulation. And yeah, there's already a very interesting, evolving literature on this. Also, yeah, a lot of recent things. Sorry? Yes, you mean to choose a different divergence? So to replace the KL with something else? Is that what you're saying? Yeah, you can do that. I mean, for the KL, you get this. Maybe for other metrics. I like that there's discussion. Go ahead. You mean if I change the KL?
No, because it's choice of the order, right? You are choosing the order. So you fix it. It's not the only.
Ah, okay. I see what you're saying.
No, they're saying two different things, but for that one.
I'm glad somebody understands the question. So, okay, one point about the KR map is that the shape of it being triangular, of course, depends on the ordering of the coordinates, right? It's very important that I first take x1 and then x2 and then x3. I mean, I could also shuffle around all the coordinates and then it doesn't look triangular anymore. But if I reorder things, then it would. And I could still use it for conditional sampling then. And so if you fix it to be that triangular structure, then it's unique. But you have to fix the ordering. Yeah. Was that?
No, that was not. Yeah. So.
Okay.
If we push it forward. Then the KL will be zero. It's zero. So it doesn't matter. Always. It doesn't matter what T is. It's always so. Okay. Right. Exactly. So that's
exactly. So it's because you choose this function class, right?
So it seems like this implies that there's only one element in that class that pushes forward.
Yeah.
So that's how you cancel anything else, and then you get a statement.
Right.
Yes. Okay. That's what you were saying. Okay. Yeah. I think I see Ricardo wanted to say something behind it. Yes, I will listen. I will keep writing at the same time. And just for the reference. Mm-hmm. I mean, there's probably a lot more papers by now. But I wanted to mention, yeah, sorry, another comment? Sure.
For the purpose of doing this conditional inference, it seems like you don't necessarily need to work with this cone. Like, so obviously triangular is very useful, but like you need just invertibility in some. So it seems like maybe you could work maybe with a bigger set, and then maybe you can minimize tail over that. Would that make
Absolutely.
sense?
So, okay, so first comment is, if you want to do conditional sampling and you want to use a map for it, it doesn't have to be the KR map, right? Like if the conditions, the H1 to H3 that I wrote down is more general than the KR. The KR is like really triangular in each coordinate, right? So it's more than we need. All you need is that the first component in the variable that you want to condition on is invertible. That's it, right? And if you want to do that, then you could choose a different set, and then you could choose a different variation of problem for sure. This is just one choice, right?
But I guess then there's no like plain answer.
Might be. That could be a future problem, right? Yeah. You need the T1 to be invertible. You don't even need to be able to invert the T2. You just need to evaluate the T2. Absolutely. I think there's many constructions that give you those properties, right? So yeah, if anyone has any ideas for a new conditional sampling algorithm, that yes, the first component not being x1, but being the thing that you want to condition on.
Yeah.
Yeah.
So there is only a single map.
Yeah, you don't need to have the whole thing to be invertible, whereas the KR map is fully invertible, right? So the KR map gives you more than you need. Yeah, absolutely. That would be interesting. There we go. We already have an open problem to work on this evening.
From one distribution, like normal F inverse of uniform, of course, doesn't, right? But F inverse of 1 minus uniform also. So maybe 2, but they have to be one of them. Yeah, but yeah, I mean, depending on the distribution, I think it, yeah, I mean, yeah. So this is, it's not unique. Yeah, maybe.
I mean, you need this unique ZY for any given Y for only the first, the T tilde 1, right?
Right.
That's all you need. Any construction that give you that, that's fine.
Yeah, and this was just pointing out that even if you say monotone, it's not.
Even that you don't need to. Yeah. Okay. Great. Yeah, I just wanted to mention 2 papers, but there's many more. Sumik is here, so any questions I can defer to the authors. But this is about triangular flows for generative modeling. And so if, for instance, now, so this is the construction of how to get KR if you're given mu and nu, right? If you want to apply this to conditional sampling, I mean, going back to what I wrote down for the Bayesian inverse problem, then your mu would be your joint distribution, and your nu would be your reference distribution, for instance. And then having this triangular map, you can then do conditional sampling, but sometimes you may not have access to the whole measure, or you will have access to your reference measure because you choose it, but you may not have access to your whole joint distribution for mu. So instead, you may just have samples from it, right? And so then you would want to construct a statistical estimator for your map. And then all these questions about statistical consistency, any guarantees, right, are very important. Sample complexity. So this is what you guys addressed in that paper, right? Feel free to add anything. Mm-hmm. Absolutely, yeah. Exactly. And then the second paper I want to mention, because this phrases things in infinite dimensional Banach spaces and proposes MGANs, which stands for monotone generative adversarial networks, where basically instead of using the KL, I think you're using Wasserstein 1, right? And then instead of computing these CDFs that go into the construction of the KR map, you use neural networks So right, and then you have also some regularization, and then stochastic gradient descent to get your map at the end. So there's many ways of how you can do this, right? But this is a very powerful framework because it allows you to also solve infinite dimensional problems, such as if you want to solve the PDE inverse problem, right? You have a PDE and you have some function in the PDE that you don't know, but you have some data, some solutions of your PDE, and now you want to invert the PDE essentially. And it's fully data driven. Okay, I could say a lot more about applications and Bayesian statistics or generative modeling, but maybe I skip that. Just to say for the flows, there's another paper. Maybe I can squeeze it here. Kelly Gunn, Niglio, Rini, and Smith. Also relatively recent, I think it was also 2024, who looked at the corresponding velocity fields. So basically triangular velocity fields in the dynamic formulation for the flows of the conditionals. And so they proposed TOT flow matching, like conditional optimal transport flow matching, to generate samples from the conditionals. And then they built an estimator using neural networks. I think that's pretty much what they do. Okay, I'm going much slower than I thought, but we had some good discussions, which is, I think, more valuable. Okay, so then how do you get KR via Brenier? So this is now where I connect KR to optimal transport. Okay, let me be hopefully a bit fast on this. So again, we have two measures. And now I'm going to fix the transport cost, but it's a weighted transport cost. So essentially, I'm going to weight each of the coordinate entries with a different power of epsilon. And I'm going from 1 to d. So you see that the x1 minus y1 doesn't have an epsilon. And then you add a power of epsilon at each time. And so you know that if mu is absolutely continuous with respect to Lebesgue, then there exists a unique optimal transport plan gamma epsilon, which is related to a transport map T epsilon. For this transport cost, it depends on epsilon. To the following problem, let me write it down. So this is inf gamma of C epsilon gamma such that gamma has marginal mu and first marginal mu, second marginal mu. And then also by Brenier, we know that this optimal gamma epsilon is actually for the T epsilon is the gradient of a convex map, right? Okay, so what Brenier conjectured some time ago is that if I look at this optimal transport problem and I take the epsilon to 0 and I look at this optimal map T epsilon, that will actually converge exactly to KR, to the KR map. And that's really amazing because that gives you a way to essentially approximate the KR, which is difficult to compute, by solving a sequence of optimal transport problems, just by taking a cost that becomes more and more degenerate. So that was conjectured, and then it was proven rigorously in a paper from 2010. But you need to assume that also, okay, so you need that to have some optimal map, right? But or maybe also for some weaker assumptions, but anyhow, let's assume that for now. So you also want that your mu, so the target measure is absolutely continuous, for that limit to hold. If that's not true, they're actually counterexamples. They showed that. So theorem, this is Carlier, we write it Carlier, Galichon, and Sant'Ambrogio. Carlier, Galichon, and Sant'Ambrogio from 2010. So if both mu and u are absolutely continuous with Lebesgue, and gamma epsilon is optimal for this K epsilon problem, let TKR be the KR map from mu to nu. And then I can also have a corresponding plan, right? then I know that the gamma epsilon converges weakly to the gamma KR. And the T epsilon converges to T KR in L2 with respect to mu. Yeah, so that's a really nice result. So this is sort of a potential avenue for developing some nice algorithms for this. But okay, so now in practice, it's actually difficult to enforce the constraints on the marginals when you solve the optimal transport problem. So in practice, when you want to solve this, one way of making it, so because this constraint, right, is the push forward constraint on the map. And so if you're solving for the map, then that's a nonlinear condition on the map. So one way of how to relax that is to basically look at self-constraint OT. I need to write the title, you have the title there. So I'm now going to write a relaxed problem. So this is min over gamma. So I'm going to have a relaxation on the target. Such that I'm still enforcing the first marginal, but I'm not anymore enforcing the target marginal. So you can think of this as basically a version of unbalanced optimal transport, because now the gamma solving this may not hit exactly the target nu for the second marginal, and it may have in particular different mass, right? So this can be interpreted as a Wasserstein proximal regularization as well. So your Wasserstein term, this is then your regularizer. And so you also get some extra convexity that helps you when you want to solve this. And of course, back to the earlier comments, you can replace this with other divergences and still do the same procedure. Okay, I'm going to try, because I know I'm running short on time, I'm going to try and summarize the paper that we put on arXiv over lunch with a diagram or with just a picture, and then explain you the results that are in there. Okay, I'm going to write it for the maps, but we actually prove it for the plans. Since we assume that mu and nu absolutely continues with respect to Lebesgue, it doesn't matter. For let's make for now the assumption that the mu and the nu are compactly supported, but all the proofs also work if you just have finite second moments. It shouldn't be a restriction. Okay, so first result is that, so again, we assume that mu nu absolutely continues, and then there exists a unique optimal gamma epsilon lambda for this problem. So that's the first thing. And actually, we can also show that this is given through a map then, like this. And here comes the diagram. So we have a T epsilon lambda that we get out of the soft constraint problem. Now, if we take lambda to infinity, we basically enforce the constraint more and more. So we should be converging to the optimal map that comes out of the original optimal transport problem, the T epsilon. And then we can take epsilon to 0. And we already know that we get the KR. So this is the result from Carlier, Galichon, and Sant'Ambrogio, right? What you can also do is take epsilon to 0 first. And what you will get is actually another triangular map, which now depends on lambda. And then when you take lambda to infinity, you get back the original KR map. Let me add a few things in color here. And I really like that you have Hagomoro, by the way. Hagoromo. I always say it the other way around. Okay, so this is optimal for K epsilon lambda. This one is an optimal map for K epsilon, right? This is KR from nu to some other measure nu lambda, which is not the original nu that we want because we relaxed the constraint. And then this is between nu and nu. So these are KR maps, right? Okay, so this is actually, I think, the first attempt to bridge soft constrained optimal transport with these triangular maps. I would also say that in practice, when you do want to get an approximation of your KR map through a soft constraint problem like that, you may actually want to take the epsilon to 0 and the lambda to infinity in a coupled way often. So now that, so what we basically show is that these two limits commute. So coupling them in a diagonal way, there's no problem. Then I would also say, because these two guys are optimal maps, they are gradients of convex functions, whereas these two maps cannot be because of the triangular structure, right? And so this tells you that actually the set of Brenier maps is not closed because you can take limits that get you out of it, right? And then I would like to mention what was in the discussion before about the reordering of coordinates, right? So if I reorder the coordinates, I get a different KR map. And for different approximations that I get out of whatever algorithm I do, I get different approximation errors depending on what ordering I choose. And so now if you have some additional information about your problem, for instance, that you have some sparsity in your joint probability measure on which you want to condition, right? Or maybe you have some other special structure, you can choose an ordering that makes use of that. And so the question that you ask, right, is like, how can you choose the ordering in a smart way? So there is another layer of optimization there. And what's really nice with this approach of coming from the optimal transport is that the epsilon essentially gives you a way of doing that, right? Like if I commute where I put the different orders of the epsilon, I explicitly control the ordering in the limiting KR map. And so I think that can be leveraged in some way. Maybe it's a way of learning some variable ordering. Okay, I'm 1 minute to 3. I wanted to tell you a little bit about the proof of this, but maybe I will just say in words very briefly that what is behind this is basically that if you have a sequence mu epsilon and nu epsilon, or it doesn't have to be epsilon, whatever parameter, converging weakly to something, right? That you have stability in the OT maps. So basically the optimal OT maps, and you also have your C epsilon and the cost. So you basically, let's say you have nu epsilon, and you have the C epsilon, right? And so there's stability in the OT maps. So if I take epsilon to 0 and all of that, you get the KR map between the limits of the two sequences. And then you also have stability in the KR maps, which is a new result that we prove, which essentially is a consequence of stability of conditioning. If you have a measure that converges, then the conditionals also converge. That's actually very painful to prove. And not that painful, but yeah, it's a bit technical, but it's not, it's conceptually, it makes sense. And then you get that also the KR maps have limits. And then, so this is how we do these two limits. I mean, this one was already shown, right? But these three are new. And if you take the lambda to infinity, this one, we essentially use the fact that the optimizer, the minimal value of this guy is always upper bounded by the minimal value of the K epsilon. And then you can use that in a way to actually take the lambda to infinity. So in some sense, our proof for the stability of KR maps is a generalization of the strategy that they used in here. What we're currently working on is actually this diagram for the velocity fields, because I think that the dynamic optimal transport and the dynamic triangular picture is sort of very useful to actually design algorithms. And at the moment, I believe there's pretty much no theory on this. And so having a diagram like that for the velocity fields would be really, really useful. I think there's already several works that are sort of looking at parametric approaches for computing triangular velocity fields. And this could give you a way of doing non-parametric approaches for approximating the KR map essentially through the triangular velocity field. Okay, so I think I will stop here.